We continue with lecture 17, part 2. We were considering damped spring mass systems. So our equation, remember, is mu double prime plus gamma u prime plus ku equals 0. Here m is the mass of the object, gamma is proportionality constant of damping, K is the spring constant. So they are all constants, all positive constants. And to write the solution, we look at the characteristic equation, which is m lambda squared plus gamma lambda plus k equal to 0. So solutions are minus gamma plus minus square root of gamma squared minus 4mk divided by 2m. So the solutions depends on the discriminant. The first case, when this discriminant is positive, this is called over-damped case. We did it in done in previous video. So now we are going to consider the second case when discriminant is equal to 0. This is called critically damped. When the discriminant is 0, it means we have a double root. So both roots are the same. I'm going to call it lambda. It's minus gamma over 2m. It's a negative constant, so it is a double root. And in this case, the solution, the first function, C1 times e to the power lambda t, lambda is this number, negative number, plus C2 times t times e to the lambda t. So e to the lambda t times C1 plus C2t. This is our solution. For the critically damped case, this is not much different from case 1. Yes, we have the t term, but as t goes to infinity, remember, exponential function is much faster. So the term with t becomes insignificant. So when you look at the limit, it is still going to be 0 because the number lambda is less than 0. So the limit of the exponential part is going to be 0. And as t gets large, exponential function increases much more rapidly. So the term with t is not going to be significant. So this is similar to case 1. Again, we have at most one local minimum or maximum. Again, it depends on the constant C1, C2, and again, depends on C1, C2, which depend on initial conditions. which depend on initial conditions u0 and u prime 0. So the initial position, it doesn't have to be 0. Of course, the initial conditions may be given at some other time t0. So typical graph again will be similar. If there is a maximum or minimum, once it reaches that maximum or minimum, then it approaches to the equilibrium. Again, there is no up and down motion. There is no up and down motion. Once it reaches the minimum or maximum distance, then it approaches to the equilibrium point. So maybe the last case is more interesting when the discriminant is less than 0. In this case, we are going to have, the roots are going to be complex. So the roots of the characteristic equation, the real part is going to be minus gamma over 2m, and the imaginary part is going to be square root of minus delta divided by 2m. Minus delta because delta is itself negative, so I take its negative to make it positive. Okay, so let me call these numbers. From case 2, I called this number lambda minus gamma over 2m. So and the imaginary part is going to be affect the period of the sine and cosine functions. So let's call it omega square root of minus delta over 2m. Then our solution, we are going to have the exponential piece, e to the lambda t, then c1 times cosine omega t plus c2 times sine omega t. Okay, now again, as in the undamped case, if we write c1 and c2 in polar coordinates, c1 is r cosine theta, c2 as r sine theta, here r theta constant. Then again, similar to the undamped case, we can write the solution as e to the lambda t times cosine of, we have r also, both in C1 and C2, we have the same r. Remember, r is square root of C1 squared plus C2 squared. R times cosine of omega t minus theta. Okay, so again, we have a cosine wave. So the period of cosine piece, again, 2 pi over omega. So omega is again the frequency, but now the amplitude is not constant. When you look at the your function, your solution, cosine is always between -1 and 1. So the function is going to be between minus r e to the lambda t and r e to the lambda t. And lambda, again, is less than 0. Lambda is minus gamma over 2m. It is less than 0. Okay, so the graph, typical graph, is going to be r times e to the, since lambda is less than 0, r times e to the lambda t is going to be a graph like this. So t, u equals r e to the lambda t. And when you take its negative, it's going to be like this. And our solution, ut, is going to be between these two graphs. So its amplitude is going to change. It has a period, but the amplitude is going to get smaller and smaller. Oh, this is underdamped. So there is up and down motion, but due to this force, which force? Due to this damping force, the amplitude gets smaller and smaller. So the mass still goes up and down, but the distance, the maximum minimum distance it goes up and down gets smaller and smaller, and in the limit it approaches the equilibrium again. So, and again, number omega affects the period. So small omega means large period, so sparse graph. Large omega means small period, meaning a more packed graph, more dense. Okay, so if this is for some omega, if this graph is for some omega, for a smaller omega, it may be like, again, we have these two curves, but it may be more. So this is for smaller, larger omega. Oh, I'm sorry. This is for larger omega. So that's larger omega, smaller period. But again, due to the damping, the amplitude, so amplitude A goes to 0 as t goes to infinity. Okay, so this is the damped case. Now, as another application, as the last application, so number 3, remember number 1 was undamped spring mass systems, number 2 damped, and for the damped we consider 3 subcases: overdamped, critically damped, underdamped. And now for the third case, we consider mechanical systems with a forcing term. So in addition to our system, now we assume that there is some external force. We assume that there is an external force acting on the object, that there is an external force, capital F of t, acting on the object, and we assume that this force depends only on time. So the position of the object or the velocity of the object doesn't affect this force. This force is an external force. It may be constant, of course. Maybe it doesn't change with time. Maybe it's constant. But at most, we assume that it only depends on time. So our equation then, general equation, mu double prime plus gamma u prime plus ku, equals this force, F of t. Okay, so this force, external force, becomes the non-homogeneous part of the equation. And in order to let me see. Oh, okay. So first, and this is non-homogeneous. I'm sorry. Non-homogeneous linear equation with constant coefficients. So you know how to solve it. U1, U2, independent solutions of the corresponding homogeneous equation. Mu double prime plus gamma u prime plus ku equals 0, and use variation of parameters to find u. Again, let me remind you how we do that. Recall variation of parameters. We write the fundamental matrix, which is the solutions U1, U2, and U1 prime, U2 prime. And we consider our solution U, we consider the corresponding system, dx dt equals ax plus b. One thing though, our equation mu double prime plus gamma u prime plus ku equals f. But remember, when we convert it into a system, the coefficient of u double prime should be 1. So we divide by m. So the non-homogeneous part in our system becomes the vector 0, f over m. And we try to find the solution by taking the fundamental matrix, multiplying it with a vector function, v, v1t, v2t. And I'm not going to go through this again, but when you differentiate and use the fact that this matrix is a fundamental matrix for the homogeneous system, we need to solve the equation, the fundamental matrix times v prime equals v. So v prime equals the inverse of the fundamental matrix times b. And then to find v, we integrate this vector with respect to t, and then our solution is the first coordinate of the fundamental matrix times this vector v. So this is how the variation of parameters work. Now, I'm going to consider a special case when the system is undamped, so that the number gamma is 0. That simplifies our equation. And the external force is cosine of omega t. It is a periodic function. The external force is given by a periodic function, but the period omega, I'm going to assume different from the natural frequency of, not the period omega, omega is the frequency. The frequency is different from the natural frequency. Remember, natural frequency is square root of k over m. Okay? Then our differential equation is m u double prime, gamma is 0, plus k times u equal to cosine of omega t. Now, solution of the homogeneous equation, again, k and m. So this is an undamped case when you consider the corresponding homogeneous equation. This is the undamped case. So number 1 in the previous video. The solutions are, we have the natural frequency omega 0. So the solution of the homogeneous equation, C1 times cosine omega 0 t plus C2 sine omega 0 t. Solution of m u double prime plus k u equal to 0. Now, the function on the right side of the equation is cosine function. So instead of variation of parameters, so to find the particular solution, u sub p, we will use a method of undetermined coefficients. Since the function bt, the non-homogeneous part, is cosine of omega t, its derivative is minus omega sine omega t. So when you take the second derivative, it's going to be cosine. The third derivative is going to be sine, and so on. So all the derivatives are going to be some multiple of either sine omega t or cosine omega t. So we write the general form of our particular solution as some coefficient a times cosine omega t plus another constant b times sine omega t. And remember, omega is different from omega 0. So this, in this general form, we don't have a piece from the homogeneous equation, solution of the homogeneous equation. This is, for the homogeneous equation, we have cosine and sine, omega 0 t. But here we have omega t, and omega is different from omega 0, so we can take this to be the general form of the particular solution. So we take the derivatives, the first derivative, minus a omega sine omega t plus b omega cosine omega t. Second derivative, minus a omega squared cosine omega t minus b omega squared sine omega t. So when we substitute into the equation, m times up double prime plus k times up, we get minus a wm sine omega t. Second derivative. I'm multiplying the second derivative with, I'm sorry. Okay, so m times second derivative. Plus k times the function itself. So the coefficient of cosine omega t is A times K minus M omega squared, cosine omega t. And coefficient of sine omega t is B times K minus M omega squared, the same constant, sine omega t. And we want this to be equal to cosine of omega t. So that means the number A is 1 over K minus M omega squared, and the number B is 0. Now remember that the natural frequency omega 0 is square root of K over M. So omega 0 squared is K over M. So the constant K is M times omega 0 squared. So the constant A I can write, instead of K, if I write M omega 0 squared minus M omega squared, I have M times omega 0 squared minus omega squared. And of course, we take omega different from omega 0. Omega 0 squared minus omega squared is not 0. So we have the constant A. So that means our particular solution is this constant A, 1 over M omega 0 squared minus omega squared times cosine omega t. So our solution, C1 cosine of omega 0 t plus C2 sine of omega 0 t plus the particular solution. Okay. Now, one thing here to notice, the significant thing here is, of course, the constant C1, C2, they are constants. So this piece, again, you can write it you can write the constant C1, C2 in polar form. So this piece has constant amplitude. Right? R, right? Which is square root of C1 squared plus C2 squared. But this piece, amplitude A depends on the difference omega 0 squared minus omega squared. If the difference is big, if there's a big difference, the amplitude A is small. But if the difference is small, amplitude A is large. And in fact, if you take the limit as omega approaches omega 0, now omega 0 is the natural frequency of the system. Omega is the frequency of the external force. So if the frequency of the external force approaches to the natural frequency of the system, the amplitude goes to infinity. And this phenomenon, this is called in physics resonance. resonance. All right, so this is when the frequencies are close to each other. The amplitude is very large. And depending on, of course, the same thing applies to some other mechanical systems. And depending on the nature of the system, this phenomenon may cause, some catastrophic results. So depending on what kind of solution you want, what kind of output you want, you need to arrange the frequency of your external force to avoid having a large amplitude. Okay, and this is so nice to get all of these physical results from, from purely theoretical considerations, solutions of ordinary differential equations. So you see, the reason we are considering this subject of differential equations is because this is only a very small application. This is a very, in this course, we unfortunately we don't have enough time to include more applications, but this may give you some inkling of why it is important to consider theoretical aspects of solutions of differential equations, because you can explain many physical situations in terms of solutions of differential equations. Okay, so this is the end of lecture 17. Next video, we will continue with lecture 18. We will start considering some linear equations with coefficients which are not necessarily constant. What do we do in that case? Okay, so until next time.